welcome to OpenCV Weekly Webinar. And today we have with us Bart Trzynadlowski, who is the winner of the US region for OpenCV AI Competition. And it is amazing what he has built, an AR/VR app with the help of OpenCV AI Kit with depth. And welcome, Bart.
Thank you.
And also with us is Phil Nelson, who is our content manager at OpenCV. Welcome, Phil.
Howdy, folks. As usual, we will be doing Q&A at the end of the episode, so please use the Q&A function on Zoom to ask your question at any point during the show, and we'll do our best to answer as many as we can. This is going to be a really fun one. We haven't really had much AR/VR stuff on here, so I'm looking forward to it. There'll also be a trivia giveaway, which will be taken from the slides. Satya, would you like to tell them what they'll win?
Well, they will win OpenCV AI Kit with OAK-D-LITE, OAK-D-LITE. And for people who do not know, we are running a Kickstarter campaign for OAK-D-LITE, which will end this Saturday at 7 a.m. Mountain Time. That's what I remember. So please, if you have not bought this, you should definitely get one for yourself and maybe one for a friend.
Yeah, at this price, you don't want to miss it. $89 still? Is that the current price to you?
That's what I think right now. I mean, unfortunately, I was traveling for the last few days. I don't know whether we ran out of the $84 one.
And the stretch goal they're working on right now is once it hits 1 million, they'll unlock the using this as a 4K, a really affordable 4K camera that looks great. Looks better than my Logitech Brio that I spent a couple $100 on, which you're looking at me through now.
Right. So it works like a webcam. And we also, as part of a previous stretch goal, we also released a case, and it comes in 4 colors. Can you guess the colors?
I have no idea. What are the colors, Satya?
R, G, B, and D. D for dark.
Smart.
All right. Okay, let's get started with this. Bart, welcome again.
Thank you.
If you could start with a brief introduction of yourself, a little background, and then we'll get started with the slides.
Yeah, sure. So my name is Bart. Thanks for having me so much. I've been working in the AR space for like a few years now. Got started with the HoloLens in my spare time, and just completely fell in love with the technology. I ended up moving to Apple in 2018, and I've recently left Apple, where I was working on some AR prototyping. Unfortunately, can't say much more than that. And am taking some time off to kind of just get back into the space on my own and goof around with stuff. And I'm just I really enjoy the space. Anything to do with mixed reality in general, and computer vision, and that's what I'm looking forward to doing a lot of over the coming year.
That's great.
Yeah.
That's great. And you won the the North America region in OpenCV AI competition. So when did you start working on it? I mean, where did you get this idea from, and when did you start working on it?
Yeah, so I heard about the competition, early, back when, I can't remember when you guys announced it, but I seem to recall around the February-March timeframe. And originally, I actually wanted to do something different. It was something to do with visual assistants. Then I saw the previous year's winner, and I had a friend of mine convince me that, hey, like, great idea, but this is done a lot. Every time there's this sort of a competition, that's what people do. So what are you really sure you can contribute something novel to the space? And I was like, yeah, you're right. And so he, it was actually a friend of mine that kind of proposed this idea, although it's something I had thought about as well. So it instantly, when he mentioned it, I was like, oh, of course, like, like this would be a great opportunity to do this. This idea of taking cameras and being able to track a headset and the environment around it. So one of my favorite all-time VR experiences was The Void, which was a location-based kind of mixed reality. They called it hyper reality. There's, in my presentation, I'll go over, there's just so much terminology in this space, but it's all basically the same thing. The Void was this experience where you would go to a location, they'd have it set up, and they'd have like, a purpose-built space with kind of partitions and walls and things like that, but you would put on a VR headset with a backpack at the time because there were no standalone headsets. And you'd have this experience, you walk through, so for example, the Ghostbusters experience in New York, you would actually walk through a building and you would, bust ghosts, basically, right? And the key was that everywhere you saw a door or a wall, you could touch it, you could open doors. So like in VR, you'd see the door, but it would actually be a physical door mapped one-to-one. And if you saw like a couch, you could actually sit down on that virtual couch because there was a real couch there. And that just blew my mind. And so I've always wondered, since then I've always wondered, like, could this be done at home? What would it take? And back when the Azure Connect came out a few years back from Microsoft, I thought that would be, I remember thinking at the time, I was like, it'd be kind of cool to try to build something like that with an off-the-shelf depth camera. Never really got around to it. Didn't really think much of it. And then, my friend, he'd been working on something similar. He actually used to work for Microsoft in the mixed reality team, and he worked with clients that had been requesting things like that, laser tag and so forth. When he mentioned, I was like, yes, of course,
just a little bit. I think I might have just asked this question a little early because people don't know what you built, right? Some people.
Oh, sure, yeah, we can get right into it. Yeah.
So let's start this, and then people will get a better idea of what you have built, and then the inspiration behind it.
Totally. Okay, I'm going to optimize for video and see how this goes.
Yeah.
Let me just full screen here.
That looks great.
Wait one sec. There we go. Looking good?
Yeah, yes, great.
All right, so again, my name is Bart Trzynadlowski. I'll be talking about the VR laser tag prototype that I built for the OpenCV AI competition. We went over a little bit about who I am, but basically here's, my contact information. Feel free to get in touch. I've been really interested in virtual reality, augmented reality. So here's, for example, HoloLens and computer vision. And most recently, I was with Apple, no longer there, on my own, Freebird for now. And in this talk, I wanted to go over a few things. First, we'll talk about like what mixed reality actually is, what that term means. We'll spend a little bit of time discussing location-based VR because that's really what the basis of my project was. Then I'll go over the project itself, and maybe we can segue into discussing what I think the future of mixed reality is. So mixed reality, what is it? You've probably heard of physical reality. We all inhabit it. That's obviously the real world, and on the other end, there's virtual reality, where everything is simulated, everything is virtual, everything that you see has no correspondence to reality whatsoever. But in between, there's kind of this broad space where you can have some mix of digital content and reality. So augmented reality is a common term that typically refers to overlaying information over the real world in some context-specific way. So for example, imagine smart glasses that when you look at things, they give you information that's rendered where that object is in your line of sight. And you can kind of dial up the amount of virtual content, and there's lots of different names that people use it. There's absolutely no industry standard to this. Sometimes people refer to augmented virtuality. Almost nobody actually uses that term, but that would be, for example, augmented virtuality. You can imagine as like a VR experience where there are physical objects that you're manipulating in the real world that either appear in a virtual form in VR, or maybe even are actually passed through, so that you're in this VR world, but when you pick up an object, the object is actually a video feed of that object, if that makes sense, kind of like matted into the environment. So you can imagine this whole spectrum of being able to like bring in virtual objects until you're completely surrounded in virtual reality. And mixed reality really is kind of a general term that some companies like to use, like Microsoft pushes the term. That's that whole space in between. So having digital and virtual objects. So an example of that, for example, is this is a HoloLens game that I made back in 2018, I believe. And you can see it takes place in the real environment. And typically when we use the term mixed reality, the key is that there's some sort of interaction with the physical environment. So all these objects are, holograms rendered in the headset, but the headset has an understanding of the environment. And so things are actually reacting and responding to the geometry of the world around it. Likewise, you can kind of imagine extending this to virtual reality. So here's like an example of like, say, a person in their room playing a VR game. And what I've shown here is that everywhere the walls in the living room were, there's now like a virtual wall, right? And the furniture has been replaced with these kind of just box-looking things, right? So the idea here is that you create a virtual environment that corresponds like one-to-one physically to the actual environment. So that's another example of what you might call, a mixed reality experience or augmented virtuality or whatever. I tend to just refer to this as like mixed reality. I think it's on the spectrum still. Right. And I think in the future, there won't really be this distinction between AR and VR. I think it's all going to be just one kind of fluid spectrum. And that's kind of where we're heading.
So just to say it one more time so that people, if you go back to the old last slide.
Yep. Oops. See if I can play this video. Yeah. Or you mean back to the mixed reality slide?
Yeah. The previous one where you were showing the boxes.
Oh, you mean here? When it transitions, sorry, this is a video.
Right. Okay.
Yeah,
so
right here,
I want to make sure that people did not miss out that this, these boxes are, they are placed where there is real furniture, right?
Mm-hmm.
And what Bart is trying to do is when you have these, augmented reality glasses on, you cannot see and you can bump into this furniture, and there are mechanisms to avoid that. But this is one mechanism where you're actually putting boxes around real objects so that when you're playing these games, you don't accidentally bump into them. You actually see them in the scene, right?
Exactly.
And I just wanted to make sure that people don't miss that important piece. This is a virtual world completely, but that person represents Bart playing the game. And those boxes are actually furniture in his living room. And they tell him that, oh, these furniture is there, but you're playing the game, don't bump into them. And there are solutions out there which do this already, but they are very cumbersome. You'll tell us about those, right?
Yeah, precisely. That's well put. If I rewind the video again, that yellow line, for example, typically is how you play VR. There's like a fake boundary on the floor that you can't go past because you'll step outside. But if you are able to detect the furniture, render environmental objects over the furniture, you can kind of get rid of that boundary and let people roam freely. Because now when you see some virtual object, you're guaranteed that they'll be overlaying an actual physical object, or at the very least, you won't be tripping over things because the virtual world is lined up one-to-one with the real one. Absolutely.
Right.
Yeah, and so
that
another
makes
example.
the space not only rectangular, you're not confined to a rectangular space, but it also makes the space interesting, right? It is, you can walk around the room instead of this narrow piece.
Yeah, exactly. And yeah, so you and I'll show with my prototype that, you can imagine playing laser tag in your room now, all kinds of cool stuff. And while this talk will focus a lot on entertainment-based applications, I want to stress that there are a lot of, serious, real world like business cases that don't involve just entertainment. And I'll kind of, we'll touch upon that later on. But another example of this is a concept film by Leap Motion, actually. And they call this term mirror worlds. So the idea is like, there's reality, then you can step into this mirror reality. And so what they're going to show here is this idea that maybe in the future you have some sort of a headset that can essentially reskin your realities. It's basically the same concept as I showed, but maybe in a little bit more direct way. So you can see here the person is re-rendered in a different way. The environment is completely re-rendered, but it corresponds to the actual physical space, right? So it's pretty much this is still pretty novel territory, but there's a lot of interesting potential here to really kind of make experiences that are very, very interesting and free roaming. And so that's kind of what location-based VR is typically about. You go to these places, you strap on a backpack computer and a headset, and then you go, play. Maybe it's a laser tag game, maybe it's some sort of adventure experience. But you can see here on the right in the split screen kind of photo, there's like a pretty, bland looking environment, but there's geometry there. There's some sort of like a fake car in the background and so forth, so that if people walk over, they can actually touch it. And then what they're actually seeing is a virtual environment. So the problem with these is that they require incredibly expensive setups. So typically what's used are OptiTrack cameras or Vicon cameras. Those are two brands that are very, very big in this space. This is a demo by OptiTrack. In this video, they're doing, these cameras were designed for motion capture. They're used, for example, by Hollywood and so forth. You can see the quality of the capture is really good. Like when these dancers are dancing around, they're studded with markers, and the system captures things very accurately at very low latency. And this is actually the solution that's used in a lot of these location-based VR systems. But if you look in the background, the number of cameras is huge, and these cameras cost thousands of dollars each. So for example, the Void VR experience, their capital costs were on the order of $500,000 per location just to build the location. So, that rigging that you see up on the ceiling with all those cameras, these things can run into the hundreds of thousands of dollars. It's extremely expensive, and it definitely it creates a barrier to entry for people that want to try to use this technology. So that was kind of the motivation. Is like, it's always been, hey, can we just use something like the OAK-D, which is a $200 camera? Why can't we just put a few of those around, and see what happens? So, my system,
just so that people know, the technology behind OptiTrack is basically they have these markers with very reflective surfaces, and they have an IR. They have IR illumination, which really brightens these reflective surfaces. And then you have IR cameras, which block out everything. And so, you see these blobs in all the cameras very easily. The segmentation is done for these blobs automatically because it's IR camera, very reflective surfaces of these balls. And so then you do triangulation, right? These cameras are calibrated. You do triangulation to figure out the 3D position of these blobs. So basically the difficult parts of it are solved by using IR illumination, reflective surfaces, and the camera IR cameras, and then it's just a matter of triangulation, but still very impressive, right? It's very simple in some sense, but still very impressive.
Yeah, exactly. Well put. Yeah, you can see that the dancers here have these little balls on them, and those are the IR reflective balls that are picked up by these cameras. Exactly, and they're all synced together, and they produce results very quickly. And so they also have a solution which includes active tracking targets. They actually have solutions where there's IMUs that you can put on yourself with the reflectors that improve the latency and the performance. But yeah, very, very cool. In a way, simple, but the cameras are just ridiculously expensive. And so I'm proposing here, Bart Trzynadlowski is what I named it last night, finally. Is just using a simple, just can we do this otherwise? Now,
it's such an evocative name. Can you go into the, why you would call it that? I just don't get it.
Well, yeah, I mean, it's my replacement for OptiTrack. It's a poor man's OptiTrack is what it is. But now, to be fair, this is obviously, OptiTrack is miles ahead still, and you'll see that this prototype is still has quite some limitations. But I do think though that it's not unreasonable to expect over the next, say, 5-year time frame that the gap between something like OptiTrack and these cameras is going to rapidly close for certain kinds of applications. Even already, people are starting to look into using just computer vision for motion capture, right? Using body pose estimation and so forth. These algorithms are getting better every year, so there very well will come a day at some point where things like these kind of very specific solutions like OptiTrack might not really be, that economically viable anymore compared to just, off-the-shelf depth cameras. So this is just a video of the project. I'll actually turn the volume down. So this is just a short 2-minute summary of the project. You can see I'm using.
Yeah, you're kind of dropping out with the audio there, Bart. I think it's noise canceling you.
Okay, I'll just turn hopefully you can hear me now, but basically, yeah, I'm showing, kind of how this system works. In my case, I just used a couple cameras. You'll notice I have a few markers on the walls, and here I am synchronizing the headset of the cameras. And once everything's done, I can actually touch, the walls, and they are where I expect them to be. I use a machine learning model to segment out certain kinds of furniture. Unfortunately, I didn't have, it trained for every type of furniture that I had, but that's why there's a suitcase in the middle of the room, because that was one of the classes that the model picked up. And you can see here that, it's detected those, it's rendered boxes around them, and then I'm able to avoid obstacles because I can see them in VR, and then I can go up to walls, touch them, and so forth. And one of the coolest things about this is that this automatically makes co-located multiplayer possible, meaning 2 people in the same space. That might not seem like such a big deal, but it's actually something that Oculus Quest, the headset that I use, can't do out of the box. They still haven't enabled this. If you've got 2 people in the same room, typically you're essentially in completely different virtual worlds. It's very hard. It's still kind of a hard problem to synchronize these headsets together. But I'll explain that because of how my system works, it actually makes it like almost trivial to add in other players because they're all being independently synchronized to a external reference point. So this is essentially what I built. This is the upstairs living room in this home, and I was able to play a multiplayer laser tag game using just a couple of OAK-D cameras basically. And here you can see I'm looking around. You can see that the walls correspond directly to my physical reality. So that's the project. Now, I won't go into too much technical detail. It was a very rough prototype. So this diagram I included in the final report, and you can see it's kind of a Rube Goldberg machine of like duct taped, Python scripts and things like that. But the general idea is not too complicated. There's basically a server process. It has the cameras connected to it, and the headsets, wirelessly communicate with that server. The server is tracking things with the cameras, and it establishes correspondence between the cameras and where the VR headset is, and we'll go into that. The main challenge here was how do you actually figure out where the headset is in the camera's perspective? That is not a very easy problem, and there are some existing solutions that people have for this. They're a little bit clunky. Now, this is really cool stuff, but you can see that the calibration procedure here is very, very unusual, right? Like it basically involves, unfortunately this video I think keeps cutting out, but it basically involves like standing in a particular location and then kind of going back and forth with this phone camera and then actually manually like adjusting. So you can see he's actually manually positioning where the controller should be. Now, this is not really practical. You couldn't run a laser tag venue like this. Like it's just an impractical calibration. It's not very precise, but this is good enough for the application here, which is what they want to do is basically make like a kind of like a blue screen type video where you'll be able to see him playing in VR with the actual person overlaid on the video. But for our purposes, that's not enough. So I had to think of a better way to do it. And after some thought, I realized that the way to do this is involving the controller. The reason is that Oculus happens to publish a 3D model to scale of the controller, so you know exactly where its origin point is. The headset tracks the controller optically, and it's very precise. So the controller actually has like a series of infrared LEDs that are invisible to you, but the cameras can see. So they have a really good idea where the controller is. It's very precise. And because we have a model of it, you can actually train one of these model tracking, detectors to pick it up. So I can pick it up with the camera. And because the headset knows where the controller is and I know where the controller is, we can then kind of work backwards to where the headset is. It's just a matrix multiplication, basically, to figure out where the headset is at the moment that you perform the calibration. So what's basically happening is the headset is transmitting like where it sees the controller in its local space. The camera is detecting it in its own space. These are two separate spaces. You capture a series of points, and then you run a solver. So it's something similar to ICP. Basically, it's a point registration problem, and there are libraries out there that can do it. And the nice thing is that you know exactly which point corresponds to which in time. So, like in my case, I actually click the button a few times, and each time I click the button, the headset sends over, where it saw the controller. And then when I receive that message, I grab the last snapshot of where I saw the controller from the camera. Then I have a series, an array of 2 points. You only really need 3 or 4 points. And then you run the solver that will produce a transform matrix that allows you to go between the two spaces. And that's it. And from that point onwards, the headset actually tracks itself in an open loop fashion. The headset itself has obviously inside out tracking. This would be better if I can continue to track the headset, but that's a little bit impractical because of how small it is. There are probably some solutions that could be done, but for this prototype, from that moment onward, the headset tracks itself. The camera is not trying to observe the headset. It doesn't need to. Once it has that initial reference point, the error is fairly minimal over time. And we can leverage the fact that the headset itself includes a SLAM system, a localization mapping system, where it's trying to optimize and minimize its error over time. So the drift never gets too large.
That's very clever. I remember when I was, we were judging, I was part of the judging team for the regional prizes. It was very clever.
Thank you. It took a while to figure out like how to do it. But it's really, as far as I can tell, the only solution. And you could actually use this trick. I think you could, for example, I was thinking about putting markers on the headset itself.
Yeah.
And the nice thing is, the problem is that the headset, there's no model for the headset. So it would be a real pain to try to measure to figure out where exactly the origin point is inside the headset. That's the big trick. And the headset itself is very symmetric, so it might be a little bit difficult to track. But you could imagine putting little, kind of like those OptiTrack balls, maybe colored balls on it, and then using the controller trick just one time to establish, a map, like to figure out where the headset's origin is relative to those tracking targets. And then you might be able to actually track the headset itself directly. So I think the controller trick could actually be used to bootstrap a more robust outside-in tracking system if you needed to.
So how did OAK-D know the orientation of the controller?
Yeah, so that I actually ended up using Vuforia. That's the only in the amount of time that I had, it was the quickest way to do it. So Vuforia has a solution where you can essentially upload a model. It can be an FBX file or whatever. They support a variety of models, and it'll essentially train a detector that attempts to locate the object in a frame, not only just to locate it, but actually to match its pose in 3D. Nice. They minimize the reprojection error. So they actually will, it's like they'll actually re-render the controller in the frame, and they want to minimize the kind of pixel error between the rendering and the actual controller. So they actually detect the 3D pose of it. The Vuforia solution it's pretty good for certain things. It wasn't that great for this. It worked, but it could have been better. And I think that, given more time, I would have tried to train my own model. Now that's a pretty tall order. There are some example architectures out there that could, it's definitely not, it's not trivial. These kind of solutions exist inside of, big corporations. A lot of companies have this kind of thing going on. I mean, Oculus themselves, I know they have models like this for like keyboard tracking and things like that. I believe there's a model called Pix to Pose, which would be probably a starting point for that. But it would have been, that alone would have probably been, a several month, if not longer project. But it is within the realm of possibility. And I expect that probably the next, year or two, there will be more. I think even just in the last year, there have been models published that can do this publicly. So, it's technology that exists out there, but given the time constraints, using something off the shelf like Vuforia was the way to go. And so, and that also is why the program itself was so complicated. Like it was this Rube Goldberg machine of different processes that were communicating. The reason was that it was kind of hard to integrate all these different components together. But
you just had 4 months for it, right? You just had 4 months. You just had 4 months for it.
Yeah, exactly. I had, and unfortunately, I had less time to spend on it I had some other things going on, but 4 months goes by really fast. And when you are just kind of doing this, in your spare time every now and then. So, yeah. But the solution was sound. Yeah, absolutely. You could train a model to do that, and probably an even better, more robust model to do that sort of tracking. So once you have this ability to determine where a headset is with respect to a camera, you essentially get multiplayer for free, because every headset, they're not trying to detect each other. That's what Oculus Quest would have to do if they wanted to support that. They would have to merge the two SLAM maps together, which is fairly complicated to do and can be kind of error prone. They don't have a solution yet that's robust enough they feel confident releasing it. But here we actually get it for free, because every headset is communicating, or essentially is referenced to the camera, right? So all we have to do is so anytime the headset transmits its pose to the server can translate it to any other headset's pose based on how that headset was registered to the camera. And that's it. And then essentially all the headsets know where they are, because they're getting those other poses from the server. So multiplayer essentially happens for free, which is really a nice side effect of this kind of system. You have a common reference point. The headsets aren't trying to detect each other. You've moved the problem over to, all you have to know is where that fixed reference point is. And now you can render all the other headsets, all the other people as avatars in real space.
Right.
I'll skip over this slide. This just kind of goes over that. Basically, what this is showing a timeline. If you moving downwards vertically is increasing time. And the idea is that like the first headset on the left sends over its pose in its own local space to the server. And then immediately after, that server broadcasts headset number 1 over to headset number 2, but it's performed a translation of the space into the headset 2 space. So when headset 2 receives it, it's received headset 1's position in its own local space. And then vice versa, the process they just keep bouncing each other's positions back and forth. And that's how they keep track of each other over time. The next big thing, of course, is the environment and how do we capture walls. So I ended up using like one of the simplest solutions possible, which is April tags. And the nice thing is that unlike something like OptiTrack, with OptiTrack, you have to know exactly where your markers are. So you have to have like a schematic of your wall. if you want to bring in a wall into an OptiTrack or a Vicon system, you have to know its exact dimensions ahead of time, and then place the markers in a very specific portion of the wall to make that work. Typically, that's how that's done. I mean, you don't have to, but that's basically how it's done. Here, I just wanted to have something really simple. I just slap up a marker anywhere on the wall, and then I essentially use that plane of the marker as the wall. And then when I see a few of these markers, basically I just create a series of walls, right, and it defines the convex space. And with a little bit of a little bit more work, you could make this, I think, work for pretty general layouts. So April tags are just detected using the RGB capabilities of the camera.
Yeah.
And now originally I wanted to use the depth, the point cloud itself, the depth data. The reason I didn't is that you can see here, and this is actually a really good case, one of the better cases. It's a little bit tough to detect the walls with passive depth if your walls are featureless. So the OAK-D cameras, they don't use LiDAR. They don't have an active projector that's bouncing off of the walls and detecting the distance. It just has a stereo array of cameras, and it's looking at the disparity between the two cameras, kind of the way your eyes work to figure out how far everything is. And that's pretty good if you have textured features. So you can see like the couch and things like that were picked up pretty well. The ceiling, for example, here is completely missing. In fact, the ceiling occupies a big chunk of the frame, but it's completely gone because it's all white, and the cameras just don't have, there's no feature points to match up, so they can't figure out the distance to it. It's effectively invisible to the camera.
Yeah.
And that typically would happen in the room that I was testing in for walls as well. Now, in this case, ironically, you can actually see some of the walls, and that's because the lighting is fairly stark. So this was later on in the day. You can see there's shadows, and I've turned on the track lighting. So I've created some features on the wall that it picked up. But you can see over to the bottom left how the wall kind of below the window is just completely gone.
Yeah.
And that's kind of the general case. Like in general, you can't rely on this because you might have a situation where lighting is fairly uniform. Your walls are a single color. They're not going to be picked up well. And when we kind of zoom in this point cloud, you can see there's a little bit of error as well.
Yeah.
Now, I think that if you put a bunch of if you just drew a bunch of stuff all over your walls, like you put a bunch of kind of visual noise on the walls, it would work fairly well. And with an active depth solution, which I know that I believe the OAK-D folks are working on, it would also be completely viable. So then you can get rid of the markers altogether. But printing out an 8.5 by 11 April tag is no big deal, and it was a really elegant way to do it quickly.
The April tag you detected on the device, right? It is working on OAK-D itself, right? Or is it outside?
I didn't put it on the device itself. I used a C library that's done on the computer itself. But you could. So the OAK-D has, of course, the processor on it.
Yeah.
I believe you could probably do it on that processor itself, the Intel Myriad chip that's inside,
Yeah.
which would make things a lot better. So the nice thing is that in an actual deployed scenario, you would definitely want to do that because that would allow you to put more of these cameras up and then attach them to much more lightweight compute systems than like a desktop PC. But I actually ended up just doing it on the PC because it was quicker to get up and running. But absolutely, you can run a lot of these models on the camera itself. Yeah. So.
And the camera you're mentioning with active, this is a very common problem with stereo vision, right? When which doesn't have active. The one that you're mentioning, OAK-D Pro, it will be released sometime next year, and it will have active illumination, so that it will be projecting infrared onto the wall, even if it is a completely flat wall. You'll be able to get the depth, right?
Yeah.
Yeah.
Yeah, really cool. I'm really looking forward to that. It'll be great to have that sort of thing out there, and as open as these cameras are, that's a big deal. Really cool stuff. So lastly, the object detection, I used a model called MaskR CNN. Due to time constraints, I just kind of grabbed a pre-trained version of it that had a number of furniture classes already in it. Not all the furniture that I would like, but it had enough. So it had like sofas and tables and things like that, potted plants and so forth. So you can see here it's detecting them. So it actually performs two kinds of detections. It performs it finds a 2D bounding box in an RGB image, as well as pixel level segmentation information per instance. So like it'll tell you which pixels belong to which detected objects and what that object is. Now using that information with the point cloud, so what you can line up, if you can project the RGB frame into the point cloud, and then figure out where those label, like which points, which depth points correspond to these labeled pixels. And that gives you like little 3D point clouds of the objects themselves. And then you can fit a 3D bounding box to that. So that's how the object detection works in that case. And it turned out to be it worked quite well. I was actually quite surprised, and it would get even better if I had more cameras, because I only had 2 cameras at one end of the room. So there's some volume of the objects missing, but it still came out quite good. If you had more cameras around the room, you threw in a few more, kind of covered the perimeter, you'd be able to kind of fuse those point clouds together and produce even more high quality detection results, which is really exciting. So you kind of get that benefit for free almost. And so, now room for improvement. This was I have to stress, this was a fairly, it's a prototype. Let's put it that way. It's held together with like duct tape and glue. I think for me, I wanted to prove out the concept, and I was very satisfied that I did that, and I think that there's a lot of potential to make this better, and even potentially build maybe even like a commercially viable laser tag solution. Especially if you're designing your own laser tag spaces, that gives you even another degree of freedom to make these experiences really work.
Actually, there is absolutely no reason to apologize. This is exactly how the creative process works, yeah. Right? You build out the prototype using duct tape and glue, as you said, and then once everything works, you have proven the concept, then you go and build something industrial, right?
Exactly.
Yeah, we talk about this on the show a lot. There's a lot of value in this kit bashing of, just taking off the shelf parts and kludging them together to get something that actually works. You're just de-risking the solution there,
Exactly. Yeah. That's how. Yeah. I mean, that's how a lot of prototyping is done, even inside of industry, right? And it's
Apple, for example, when they invented the mouse, they literally went and one of the Apple engineers, he went outside, went to one of the CVS or Rite Aid, whatever store, and he got a deodorant with a ball. Yes, it's a true story. And he popped out the ball, and that served as the initial, for prototyping.
Wow. In San Francisco, it probably would have been a Walgreens.
Right. And I think I read the story. There is this website where Andy Hertzfeld, who was on the
folklore.org is what you're talking about.
That's right. I also have the book. Revolution in the Valley, I think that's the name of the book.
Fire in the Valley, maybe?
Revolution in the Valley. But folklore.org has all the stories. It is basically the website which has all the stories in the book.
Yeah, I mean, it's like the key to being a good prototyper is to be able to, to do the minimum amount of work possible and leverage the stuff that's out there already. In industry, you'll even see what they call paper prototypes, meaning like you might want to prototype some sort of a digital product, maybe it's software, maybe it's some, hardware thing. But the question is, can you just do it? Can you mock it up with like a piece of cardboard? You know what I mean? Like, can you, for example, like if you're doing something with AR, do you actually need to, have like an AR headset or whatever? You have to go buy a HoloLens and do something. Can you, perhaps just, try to mock it up with something physical instead? Really, really cheap, low cost solutions, perfectly valid. And it's really about getting the most bang for your buck, right? And so absolutely, like it's a skill. It's definitely a skill to not go too deep into a problem and kind of realize what are the important contours of the problem that have to be shown without necessarily trying to like really, zoom in and build a technical solution. And so it can be a tough balance to strike, but when you've got a time limit, you definitely will end up erring on the side of simplicity.
I want to slip in one more story. So this is from Richard Feynman. When he was working as a physicist, he went from Princeton to, I think, MIT. And in Princeton, they had this particle accelerator, which was, very badly held together. If you went into that room, it was all, wires everywhere, and it was very messy, right? It was extremely messy. And when he went to MIT, there was this pristine, or was it Caltech? I can't remember which one, but another institute where it was pristine. Everything was nicely organized and everything. But when he looked at the papers coming out of the two, there were vastly more papers coming out of Princeton than MIT. And he reasoned that, the problem is if something went wrong with this, complete which almost looked like a prototype, people could go in and quickly fix it, right? They did not need any engineer to come in and fix it, right? The physicists themselves could go and, oh, I know this thing is loose or whatever I need to do, right? So it was a very hands-on process. They knew their system very well. But on the other hand, the MIT kind of system, which was pristine and nice and covered and not open, it was difficult to work in the sense that, oh, it looks very clean. But if something went wrong, they could not fix it themselves. They had to get people to fix it. And all those things, it creates this mental barrier. When you have your system and you know it, you can manipulate it, it makes a big difference, right? And that also,
you don't want to become a slave to the system, right? Like that's also another thing too, is that if you've built this, big edifice of technology, and you need to, and maybe it's not working right. Like the more you've invested in that technology, the more you try to work in the way that that technology wants you to work, right? As opposed to, maybe there's a better way to do it. Maybe you have to reconfigure things dramatically. But if it's this complicated, structure that you've built, you're less likely to want to do that, and you'll essentially close off a lot of paths of exploration because, well, that's not how this thing is supposed to work. This is how it works, and I have to maintain it this way. And that, so the bigger something is, right, the less nimble it is, and the less you're able to, kind of tear it down or completely reconfigure it and so forth. And that's another value of having something that's, very loosely held together, something that you're not going to want to release. That you don't feel bad about tearing up and ripping apart over and over again.
Right.
Yeah, absolutely. Yeah, definitely valuable lessons. It's at the end of the day, like results are what matter, and to at least to get things moving, right? And so even if something's not technically the most attractive solution, if it doesn't meet all the best practices, so to speak. But if it's actually working, that's, it's like the old adage, right? A bird in the hand is better than two in the bush, right? Actually having something working, even if it's not the kind of perfect thing, or doesn't do more than everything you want it to do, having it do something well, as opposed to, chasing this potentially, kind of further off, bigger return is always, I think, better. So yeah, but there's still a lot of room for improvement, and potentially something that either I might do or other people might want to tackle. But the first thing is, of course, this improving the camera and the headset synchronization. And I mentioned something earlier about potentially developing solutions that allow the headset itself to be tracked. So one of the key problems here, by the way, is that unfortunately, the sad thing about the mixed reality space is that things have changed a lot since like the early days of computers in the 80s and even the 90s, when computers were kind of just taken for granted as open platforms. I think once we got into video game consoles, mobile devices, and then onwards, companies realized that they could really kind of lock down these ecosystems and maintain a really, really iron grip over what software you can deploy, over what the experience looks like. It's kind of done in the name of experience, but there's a big trade-off here in openness. And that's definitely the case with these headsets for various reasons, including the fear of being perceived as violating privacy. So for example, Facebook is extremely sensitive to the criticism they've received over privacy, with good reason, obviously. And so they kind of don't want to mess things up, and so they've been very careful about restricting camera access on the Oculus Quest. You just can't get it as an application. That's both for performance reasons. They don't want you running algorithms on something that really can't sustain it for a long amount of time. It would degrade the experience. But also it's to, try to kind of, I think, shore up their image and make people feel more comfortable wearing. Because like I have a Quest right here. I don't know if people have actually seen one up close. I don't know if you can see this in the camera, but there are 4 cameras on it. And, I think people are naturally a little bit concerned about wearing a Facebook manufactured device in their home with lots of cameras all over it.
Right.
So as an application,
well, they did just launch those Ray-Bans, though.
It's true, yeah, they did, absolutely, yeah. But I think they tried to be careful with that in terms of the active recording light and so forth. But yeah, it's a big experiment, and actually the entire industry is watching because this is kind of a point of contention inside the industry as to whether the world is ready or if it's even desirable to allow this sort of recording. And Facebook kind of just went headlong into it, betting that people won't care. Snapchat did so earlier, to be honest. It was actually Snapchat that started that with their spectacles. People are trying to see if that kind of Google Glass backlash will happen again. So they're, everybody's kind of watching, with bated breath to see what happens with this product, whether it'll make a splash or not, or whether it'll generate controversy or not. But for the time being, I think for the next several years, in terms of commercial, like big commercial headsets, I think it'll be relatively unlikely that camera access will be made available to developers. Eventually, it'll have to be, because there's going to be a point soon where it's really going to gate the kind of experiences you can build. But for now, it's a problem. You can't. That would be the easy solution, to be able to just track markers from the headset itself, but you can't. So, improving the outside-in tracking is one thing that could help here. And there's a few ways to do that. It might be a lost cause though, because maybe in a few years, like I said, that'll eventually be possible anyway. So it might not be worth the effort. Yeah, and so that closed loop tracking, that would enable closed loop tracking, meaning that once I've established that correspondence between the headset and the camera, I'd like to be able to continue to track it, so that if there's some sort of an issue, like if the headset loses tracking, sometimes they actually have tracking issues. Something happens, we can quickly continuously improve that error and continuously track from that external reference point. That might be especially valuable for a large scale laser tag game where people are running around. Who knows what they're doing with their headsets? Maybe they take them off for a moment, the application restarts. You would want to have some way to kind of continuously track. Body pose tracking, that's an obvious one, and that's actually a low-hanging fruit. People, other projects, in fact, for the OpenCV competition demonstrated, pretty good body tracking with the OAK-D cameras, and you could easily throw that in there. Like I know where you are roughly because the headset's telling me where you are. I can, evaluate your body pose, and if I had multiple cameras, that pose would be even more accurate. And then we can render avatars that kind of move around like people do, with limbs and so forth. Using those external cameras, which is really cool, because that would be that's right now, no headset can do that. They don't have the cameras in the right positions to do that. And who knows when that'll be possible. So that's a low-hanging fruit right there. And lastly, dynamic object tracking. So just running that object detector more frequently to allow for, imagine experiences where you have like movable props. That would be pretty cool. Being able to hide behind a movable barrier, or maybe being able to pick up certain kinds of objects like a fake sword or something, in conjunction with body tracking, you might be able to do some really cool stuff there. So, oh yeah, and of course, the big one though that I alluded to is inside-out mapping. So being able to do this stuff from inside the headset, which is, so looking out on the world, which kind of is a nice segue into the final thing I want to talk about, which is, what is my view on the future of mixed reality? Now, this is, I can talk about this all day, so I'm going to focus specifically on that part of the spectrum that's closer to virtual reality. We're talking about like where are VR headsets evolving. I'm going to ignore the discussion about, transparent AR, like the HoloLens. I have one here. I don't know how many people have played around with these devices, but this is one particular vision of the future where you have, some sort of a glass-like device that you wear on your head. And the images are actually formed by projecting light into a waveguide that then bounces into your eye. It's a really cool idea, but I think in the end you'll have like a spectrum of devices, but specifically focusing on the heavier end where you're looking at VR, really trying to change your environment and so forth, and applications for that. I think the big thing that we'll see coming forward. I'm
gonna interrupt you there real quick, Bart. Since we're coming up about 10 minutes left, we want to make sure we get our trivia in before, because some people have hard meetings right after this, and so we want to make sure that everybody has a chance to win. Satya, would you like to tell them what they'll win if they answer our trivia question correctly once more?
Yes, they will get OpenCV AI kit with depth, light, OAK-D-LITE. And I just want to be very upfront that people will receive this when the Kickstarter campaign people start receiving there. We don't have these units lying around. There are only a few units. So you will receive your unit when other people in our Kickstarter campaign get it. So that could be a few months from now.
Yes, absolutely. And so if this is the first time you're joining us, the way this works is I'm going to ask a trivia question, which I've taken from Bart's slides here. And the first person to answer this question correctly in the Zoom chat window on my screen will win the incredible delightfully diminutive OAK-D-LITE. So earlier in the presentation, Bart talked about an industrial system that's really often used. It has a whole bunch of different cameras and little balls and stuff. What is the name of that system? All right, who was Johnny on the spot this time? I'm looking through here. It looks like Pedro. It's like Pedro was our first one to answer correctly, which was OptiTrack.
Nice. Congratulations.
Congratulations, Pedro. We'll be in touch. Please go ahead and send an email to phil@opencv.org, and we'll make sure that when devices ship, you get one of them. All right, go ahead, Bart.
Yeah, I'll just wrap to bring this home now, and that is with I think what's exciting here for people. This is OpenCV, right? So people are excited about computer vision. I think what you'll see a lot in the coming years is cameras, and already what you'll notice is that every VR headset now is increasing the number of cameras it has on it. That's for tracking as well as for what they call pass-through. And so in fact, these three headsets that I've shown right here, the Vario on the left, the upcoming Lynx, which is a Kickstarter project, it's an open headset that I've backed, should be pretty exciting. And the Vive, I believe that's the Vive Focus. They all have, and including the Quest as well, they have a pass-through mode. And that's been pretty interesting to see.
The Index has an interesting, our friends at Arcturus Industries, we had them as guests recently, Jeff Powers, are doing some, the room mapping stuff with some of the Index. It's pretty cool. Exactly, yeah, that's a great example. Even the Index, yeah, the Valve Index has it. The Rift S, which has been discontinued, had it. And this is the Lynx, which is coming out. The Kickstarter is running until the end of this month. I highly recommend people that are interested to back it. The idea is that you are actually bringing in reality through cameras. So when you put on the headset, you still kind of see what you're seeing and being able to render things in there. Oculus Quest has released an API to mess around with this, and this involves a lot of obviously using the good cameras. This system right here, the Vario that I'm going to show right here, has both. You can see the two RGB cameras that bring in the scene, and I believe are also used for tracking. But there's also in between, kind of hard to see, but there's what I believe are, they have a depth camera in the latest model as well. So basically, we're like, there's a lot of applications of computer vision here for mixed reality, and what you can do with it, I think, is really inspiring. And so this video is kind of cool. This is a Vario customer case that they had. It's basically like a medical training simulator. So what you're seeing here is they're in the real world. That doctor is obviously fake. He's got a fake clipboard, and there's like a fake patient on a real bed. So the idea is that you can do these kind of training simulations that really blend the virtual and the real, and are far more engaging than just for example, doing something on a 2D screen or being in a completely virtual environment. You can still kind of have like tactile feedback and so forth, and design much more rich experiences. So I think that's a pretty exciting taste of where things are coming. And Vario has a ton of examples of this stuff. They've been working in this space a lot. And it seems like all the standalone headsets are working on this. Quest is increasing its access to that pass-through API. Obviously, I'm sure they'll have a subsequent product that does more with that. The Lynx is betting on this big. It's going to be all about their pass-through, and that'll be an exciting, I think. Yeah, it seems like one of the big, for the last several years, it seems like the big sticking point with this has been that the cameras just weren't fast enough or high def enough. Stuff looked janky and passed through. At Occipital, we had a thing called Bridge Engine that we did some pretty cool job site demos where you could have virtual objects to train people with a iPhone headset, but 30 FPS cameras, even 60, just not enough, and the frame rate was too low, and it just wasn't high enough definition. Yeah, for sure. It's a challenging camera. Probably it's the quality of the cameras, not just the resolution, right? Like you mentioned, the speed, the ability to deal with dynamic range, of course, is a big thing, right? So you don't adjusting for different light scenarios, because the sun rises and sets. It's weird out here. Exactly, yeah, and like camera noise, things like that, and also the display side of it, right? But the displays are, I think, some of the newest headsets coming out have some pretty incredible leaps in terms of display quality, the density, and it's, if you're thinking about like a few years out, I think the space is absolutely going to explode, and there will be some sort of a tipping point where you'll really start seeing these headsets used a lot in professional and just recreational settings, because I think that this ability to do AR as opposed to being consumed in a VR world is far more attractive and more useful
for the kind of experiences where you just kind of put it on quickly, do some task, and feel comfortable doing other things in it, not just being, in some sort of a completely isolated experience. So yeah, and I think that'll open up lots of cool opportunities for computer vision. So I think OpenCV is more important than ever now. At some point, people will have access to those cameras. You'll need to in order to do the kind of compelling experiences you see here. And, so you can imagine there'll be a ton of opportunity for leveraging computer vision to, really build custom experiences that make sense for your application use case. And so I think it's an exciting time for that. And that's it. That's all I wanted to go over. My contact info, I'm always looking to collaborate with people on stuff and mess around in this space. So happy to hear from folks. And I don't know if we have time for any questions, but I'm happy to take them.
We have some time.
Yeah, definitely. Yeah, thanks again for joining us, Bart. This was a really interesting, informative. Go ahead and unshare your screen. Thanks. Way ahead of me there. So yeah, this was really fun. Like I said, it kind of piggybacks on our previous episode with Jeff Powers from Arcturus Industries, because they're similar kinds of technologies and in the same kind of field. It also goes back to my history with occipital, with the inside-out tracking, with a structure sensor and structure core. So pretty damn cool. I've already got one question answered. Andy asked, is any of this code open source? Do you have a GitHub repository?
It will be. Yeah, I do want to open source it. It might take a couple more weeks. I'm extremely slammed lately. The main obstacle is I need to remove, so the headset part of it was done in Unity. And there are some assets that I download from the Unity asset store. Unfortunately, there's licensing, so you can't redistribute those, whether they're free or not. Some of them weren't. They're very low cost. So what I want to do is replace them with just gray boxes, just because they're somewhat immaterial to the experience itself. It's really about the Python code and so forth. So yes, I do want to open source it. Keep an eye out. It'll be on my GitHub when I'm able to do that. I just have to find time. I've been a little bit slammed. So I estimate like probably sometime within the next couple of weeks, it'll probably take me a day to sit down and just strip out the assets from the Unity project, and then I'll have to go. I will warn people that it'll be a little bit janky in terms of how you build it. There's no it's a pretty manual build process and so forth. But I hope the code will at least be useful for people to look at.
You mean you didn't set up continuous integration and unit tests and everything? I'm really disappointed.
No, in fact, I won't go into it, but the project almost got derailed by that when I ended up doing it myself. I initially had someone that wanted to help out, and we tried to use Basel build, and we wasted like 3 weeks, and
wow.
We kind of went our separate ways after that. He got busy and so forth, and I was like, no more. We're just doing this the quickest way possible.
Yeah, kit bashing is sometimes the true way. There's no shame in it. It's how a lot of these innovations are made possible.
Yeah.
Roy would like to know, could you talk a little bit about the hardware you use on the server side? What kind of computer was it?
It was a pretty beefy. It's actually more than you don't need a very beefy computer for this. I think it could have ran on anything modern in the last 5 years would have been fine. I have an especially beefy system. I have a AMD 5950X, so it's a 16-core machine with like 128 gigs of RAM, 3090. None of that stuff is necessary. I wasn't using the GPU for anything. Honestly, because I do remember hooking up the OAK-Ds to my laptop, I think, as well. The most expensive part of it is the April tag tracking was surprisingly expensive because it's not GPU accelerated. It's done by the CPU, so you need a little bit of a beefy CPU. But that could be optimized. That code was completely portable, not intended to be optimal. So I don't think you need that much to run this. And the nice thing is if I moved more of that onto the OAK-D itself, which has the Intel Myriad on it, particularly for the machine learning parts, you can really get away with
April tag out of the box. You can through the API.
It's part of the API, yeah.
Okay. I think when I started, I don't recall it being part of the API when I started, so that's the reason I ended up. Yeah, but if it's there, that alone actually was one of the heavier parts. That and the CNN model, which could also be put on the OAK-D. The April, and that was only because the code, I downloaded something online that works great. It was called SWAT-Botics April tags, but it's entirely in C, very portable, great for prototyping, but it's not optimal. If that runs on the OAK-D, then you could essentially run this on anything. I think you could run this on a potato, as long as it's got 2 USB-C connections for the cameras. A potato computer could do it because there's not much to do on the CPU side other than detecting those April tags and running the model, which was, I think, GPU accelerated.
So we just need a potato and a glass of water and some toothpicks, the old classic school. Yeah.
And USB-C ports. Very
important. Right. Obviously. Yeah. So we need a bus then. We need some USB bus.
Yeah.
I think let's do one more question here. Let's see. Anrup asks, do you think this model can be adapted easily to different players such as Unreal or the HoloLens SDK, or because they all have their different kinds of ecosystems, and this was Unity, correct?
Yeah, this was Unity. Yeah, so absolutely. I mean, the server itself was doing most of the work, right? And that's independent of any of that. And I wrote it in Python, had some C bits in there and a little bit of C++, but it was mostly Python. So the actual headsets themselves were really just receiving, they're just transmitting, like their controller pose, head pose to the server, and then getting, information back on like where the walls were and so forth. So yeah, you could do this with anything. I think that with devices like HoloLens, Magic Leap, and so forth, though, you have onboard cameras and depth sensors that can detect. So HoloLens does wall detection, right? So does Magic Leap. So some of that might be a little bit moot there. Although there could be, some reason you want to do this for things like body pose and tracking other players and so forth. But yeah, absolutely, you could totally adapt this to other systems. It's not just the Unity part was the simplest part of it, to be honest.
Yeah, and there's just so many off-the-shelf parts for Unity. I use it a lot with my own, messing around with building VR stuff, because it's just so easy to drag and drop things, and it works about 50% of the time.
I even did the animations, the RGBD point cloud, and that the intro, the thing where I had the guy standing in the living room. All that was done in Unity. It's actually,
oh wow,
I actually coded up the animations with code because it's so easy to do. Like there's just a few lines of code to do the thing where the room transitions, and it's really a really flexible tool. It's you can, if you need 3D for anything, whether it's for a game or an experience or like a video that you want to make, Unity and Unreal are both really great tools. Can't praise them enough.
Yeah, our friends at Team Kauda from OpenCV AI Competition were just recently featured on the Unity blog as well for their was it synthetic data, I believe. Well, I'll add the link in the chat or something there. I think we're about on time. You want to get any last thoughts, Satya? You want to take us home?
Yeah, thank you, everybody. And thank you, Bart, for joining us. Congratulations again for winning the North America region. It's really great honor. And you're very close, for the, for the finals also, for the grand prize also. I cannot reveal the details, but very, very close.
Good to know.
Yes. And congratulations. Thank you, Phil.
Thank you.
Thank you, Phil, for organizing this, and thank you, everybody, the audience.
Thank you.
I really enjoy these shows, and we'll have people like Bart who will inspire us.
Yes, in fact, next week will be the rescheduled episode with John Keefe of Draw and Code, who makes some incredible augmented mixed reality experiences as well. So I guess it's unintentionally mixed reality month here on OpenCV Weekly Webinar.
Awesome. Well, thanks for having me, guys. I really appreciate it, and thanks for running the competition. That was awesome. I had a great time, and thanks again. I was really, really humbled to be able to win that North America prize, and it was a lot of fun. It was a great competition, and I learned a ton. And looking forward to also what Luxonis has in their pipeline.
Thanks so much for watching this episode of the webinar. Please hit that like button, subscribe, and don't forget to tap the little bell icon to be notified when new episodes drop. This week's episode was brought to you by Microsoft Azure and Intel, sponsors of the world's largest spatial AI competition, OpenCV AI Competition 2021. If you'd like to be in the audience next week, subscribe to the OpenCV newsletter.